Okay, today I'll talk about this chiral matrix model, but in QCD phase diagram, that is, temperature variant potential plane. So this is a very recent work I started with, like couple of months ago, and so the results I'll be showing you. You should not quote it, but it may change in future also. So my collaborators are Ritesh Da, Najmul sir, Rob, Yoshimasa, and Vladimir. Okay, so you know this Quark-Gluon Plasma. This for this for Quark-Gluon Plasma, like for low temperature regime, we have from say 0 to 130 MeV, we have this very successful models, say HRG model, chiral perturbation theory, and at the higher end for the temperature for above 300 MeV, we have some recent perturbation theory, and one of the most successful one is the HTL perturbation theory. And the significant contributors are this Najmul Haq sir, Aritrada, Munshi sir, Strickland, Nansu, and Andersons. But still, we have the region which is which is less explored, or which is very hard to explore with the perturbative calculations. This is the region which is near the transition region, or the for the system for the QCD, it is the crossover region. So this region is called the semi-QGP region. This is the region where like the partial quarks are in partial deconfined phase. In the perturbative region, quarks are fully deconfined, the free and the confined phase. So quarks are not free, but this is the region where you can you have some partial deconfinement. There are some free quarks and also some confined color charges. So to explain this region, I'll use the matrix model, which is essentially developed with the help of using the order parameter of the deconfinement phase transition. So how to model this how to model a theory with the order parameters. We use a background gauge field, which is characterized for the ACU3 gauge theory without quarks. For now, we can like write it as a in a diagonal form, since lambda 3 and lambda are the Gell-Mann matrices, which is diagonal, and Q and R are the some variables which will be related to the Polyakov loop. Okay, so using this background field, we can calculate the thermal Wilson line, and eventually we can calculate the Polyakov loop, which is the order parameter of the deconfinement phase transitions. And these are some variables that needs to be also like that will change depending on the which region we are in the of the temperature. Okay. So for detailed calculation, for the details, you can see this literature here by Pisarski and Hidaka. Okay. So if I use that background gauge field, and with addition to the gauge fluctuation, so our total gauge field will be that background field plus the gauge field. So right. For the fluctuating gauge field, we can calculate the propagator here, and using the standard free energy calculation, we'll get this kind of expression for the free energy. So we know that for the perturbative calculation, we get this T⁴ type of dependence on the free energy, and this constant term that you can get in the perturbative calculation as well. So, but this comes solely due to the presence of the background field, which is characterized by the Polyakov loop. And this is the form of this V4 term is given by this large expression here, and this is all the modulus term is like modulo 1, sorry. And okay, so but this is not the end of the story. The lattice calculation, lattice calculation by Borsani et al. I did not put the references here. Sorry for that. So it shows that the free energy near the transition region does not behave like t to the power 4, which you get in the perturbative calculation, but it behaves rather t square, like t square. So in the matrix model, we add this term which like we add this term kind of by hand, this kind of term which behaves like t square, and td is like if you do only pure gluonic 3, then TD is 270 MeV, which is a deconfinement temperature. But for since in the later part of the talk, I'll be adding quarks, so the deconfinement does not make any sense. I mean, yeah. So in that case, will be concerned with the chiral phase, I mean T chiral. So for now, this TD is just a parameter. I mean, TD will just be treated as a parameter in this model from later on. Okay, and this non-perturbative term also you can has this kind of constant terms, and then you can have some V4 that is given here, and also some V2. I mean, this kind of term, and that I mean that is dependent on the Polyakov loop variables. Okay, this is not important for this work that I am presenting, but just to mention, this kind of non-perturbative term can be, I mean, we have shown that this kind of non-perturbative term can be obtained if we consider a two-dimensional ghost field, which is named as thin field. So yeah, if you just with the thin field, using the standard calculation like this one, we can get this non-perturbative term. So for this, you can see these references here. Okay. Okay. So like if you do the perturbative calculation of this, I mean, try to calculate the free energy, then you will always get t to the power 4 type of term. You will like not get t to the power t square term. So to get the t square term, we add it by hand. Like, yeah.
This particular form that you are using,
yeah.
I mean, without the tin field, you could motivate that particular form. What's the motivation for this form? If you,
okay.
For V2, you are using some very particular form, right?
This V2 you're saying? Okay. So yeah. So here you have this V4, right? So V4 is like you have this form like say I am saying just QA square for now. It's some 2Q by 3. I am just saying 2QA some Q. Okay. Oh, so you will get. No. I'm just saying that if you expand it, you will get something like Q term in terms of QQ, right? So like for others also, you will have some cubic term, but that cubic term will say, I mean, have presence of cubic term will signify some kind of phase transition in the before the deconfinement phase transition as well. But there is no phase transition in the other than this in the for pure gluonic system. There is no other phase transition other than the deconfinement confinement. So to remove, I mean, there will be a problem. So to remove that, the motivation is to add such a term that will remove the effect of this first order transition. So that is the motivation to add this kind of V2 term. Calculation comes at the first power is QR to the power square. So you are inserting this via the.
You are inserting the Q and R that you wrote in the V4 equation. So you are inserting it via the Polyakov loop. So the first power by traditional Polyakov loop expression, the first power comes as the square. That is for V4.
Yeah.
So you are also considering some linear power of Q and R. That is V2.
Yeah, right.
So that's what. So basically you are taking some square root of matrix. There may be some Polyakov loop type of calculation. So that is basically generating V2.
Yeah. Okay. So now So now in this talk I'll be adding the quarks in the system. So you know, this for massless, if quarks are massless, we can I mean separate decouple this in a left and right part. For the quark Lagrangian, we can decouple it in the left and right part, right? So and this Lagrangian is it follows. I mean, it follows the flavor symmetry group also. This GF, SU3L, SU3R, and U1A. But this is when the quarks are massless. But at zero temperature, quarks are not massless. This has some, I mean, heavy mass. So if we have some massive term here, this Lagrangian is not symmetric under, I mean, symmetric under this GF transformation. The simplest order parameter that we can have is like a term that is of the form, I mean, that goes like this psi L bar psi R, and also under this GF group GF transformation under this GF, so it will also change like this. But and also for having a small mass also, this Lagrangian is like broken. This E1 symmetry is broken by this to Z3 asymmetry, and that can be seen if I have some like date phi term. Then after the transformation, you'll have some e to the power 3 I3 alpha, and you know this will be only identity when alpha is some integer. Okay. So motivated from the sigma model, so we treat the phi as some scale, I mean, as some complex non-net field, which is expressed by this Gell-Mann matrices here. And so the linear sigma type model for the phi field will be given by this these terms here. Then m square for the mass term for the phi field. Then this is determinant term that will cause the breaking of the U1 asymmetry to Z3 symmetry, and this is the quartic term that will also be needed. I mean, this is the standard I think sigma model type of potential, and but still this is symmetric under SU3L cross SU3R. So to break the symmetry explicitly, we add a term which is linear in phi, this kind of VH of term, and where H is like proportional to some current quark masses, and it is diagonal. Okay. And so now that we have phi field, so in this chiral matrix model, the novel features is that in the quark Lagrangian we include some interaction between the phi field and the quark field. So basically, this is the point where you can see that quarks will be affected by the gauge field as well, gauge field from the D, because this is the covariant derivative, and also by the phi field. So if we calculate from that from this quark Lagrangian, if we calculate the free energy at zero temperature, you will get some terms like this one here, which is like quartic in or I mean it is mi to the power 4. Mi is like some that is mass that I mean no not I mean yeah, some like dependent on the Yukawa potential and the sigma field, sorry, phi field. But we need to remove these divergences. So after renormalization and for the general form of the phi, we can write it like in this V log term. Okay. Now this is the zero temperature calculation, but we need to also calculate the this free energy at finite temperature. So this is given by here V quark perturbative at finite temperature. And yeah, okay. So now, previously I have shown you a term like linear in phi that was in zero temperature. I mean that was motivated by the zero temperature symmetry breaking. But we for the physical QCD at very high temperature, the quark mass is not zero. it has some physical value. Some say for up or down, we have some 5 MeV or 10 MeV, something like that. So to get that, I mean, at very high temperature also, to get some physical mass also, we needed to add this kind of term, which is I mean, currently I cannot explain how this is, but yeah, I mean, this was motivated by this paper. And the thermal part from the quark, I mean, quark, the finite temperature contribution for the quark Lagrangian here, this can be, you know, after doing the Matsuura sum, you can get this kind of form where we have this, you can see that we have also the effect from this QA, I mean, the effect from the Polyakov loop also, and this EF that is dependent on the mf square, and this is y sigma f. Sigma f, it's diagonal of elements of the phi field. So okay, so the thermal part of the quark also, I mean, depends on both the deconfinement order parameter and also the chiral order parameter. And this above term can, after some manipulation, this above term can be rewritten in terms of this derivative in terms of this thermal part of the quark loop. Okay, so now we have to add all the potentials that is coming from the gluonic part, then the phi field part, then the quark part, and this is the extra novel part. That, I mean, this part is this term is actually in new in this chiral matrix model. Yeah. So we, after having all these terms, then actually, yeah, the new term is capturing that at very high temperature, the like chiral perturbation theory usual or sigma model, you can get the quark mass to be 0. But this extra term is going to some physical masses. I mean, not 0. Say very small masses. Say, for example, at very high temperature, you have some quark mass have some, I don't remember, maybe 5 MeV.
So is it like a thermal correction to the
Yep.
pole mass kind
Yeah.
of thing?
Yeah, thermal correction, right? Okay. So the Yukawa coupling, we actually fit it from keeping the T, like if we take T chiral, I mean T chiral to be like 155 MeV, then from like changing the Yukawa coupling, and actually so we actually fit it and got the base, I mean based value we can from this plot. So since this band region as like matches with this like this 155 MeV, so basically in for the current work I have taken like Yukawa coupling to be y to the power 5. Okay, so okay, now comes to the result part. Now having all the potential I have shown here previously, so if you calculate the susceptibilities, this is the light chiral susceptibilities. So you can see in the T mu B plane we have some. I mean, this is, I mean, I don't know how much understandable from this curve, but this has some peak here, and but and this is the region where this has the largest peak. But still, I mean, we expect some kind of in Team UV plane, we expect some kind of critical point or some singularities in some finite region. So till now, this is ongoing work. We have not find any kind of such term. This is, I mean, this is just continuous. Yeah, only peak I am getting at this end. So I am for sure we need something to fix these things. Like similarly, I have also calculated this like strange chiral susceptibilities and this cross susceptibilities, which is like sigma L, sigma S. Still no sign of some any critical endpoint in the finite region. Then okay, yeah, but at finite, in the finite chemical potential, you have some, you expect something critical endpoint, right? I mean, sorry, I didn't get it. I repulse. Oh, Yeah, I guess we need to look at that. So, okay, yeah, I mean, with that model, we are getting only this kind of susceptibilities, some continuous, yeah. How is it different for Quark-Gluon model? Okay. Okay, I am not sure about PQM models. And also this Polyakov loop, this plot, I mean, sorry. I mean, we have this is the usual form in the zero chemical potential, but at finite chemical potential, we have some little non-triviality, but still with this is the conclusion. I mean, analysis is under process, and this is some. These are some. Where? Okay. So basically, I mean, yeah, I guess, right. So PQM model, I guess we don't have any like quark and mesonic interaction is there, but in our model, we are considering that also. That way it is different. And I think this is the pressure, and also this is the condensate, that light chiral condensate and the strange chiral condensate. And this is the, I mean, this has some high values and then it goes down. Yep. And okay, so the conclusion is like, I mean, in the chiral matrix model, we have some extra interaction between quarks and mesonic fields, and we also use this extra term which makes sure that in the high temperature the quarks are not massless. We have some small mass. And also, I mean, till now, though, so we don't have, I mean, the analysis of this work is under process, so I cannot comment on that right now. Thank you.
Thank you, Manas.
Yes.
Sorry, so I'm trying to understand. So you have quarks, mesons, but no gluons. You're just freezing the Polyakov loop. You have a Polyakov loop,
Yep.
but you're not integrating over it. Is that correct? Or
No, so like for the gluonic part, we are adding these two potentials, right? Yeah, it is integrated, but yeah, for the
no, but the Qs and Rs,
yeah.
do you integrate over Q and R?
No.
Yeah. So for example, you know, like if you just had, if you just put in many matrix models, you will usually calculate, you freeze the gauge fields.
Yeah.
You know, we calculate some determinant and then you can kind of integrate over only the Polyakov loop part of the integrand. Okay, just do the matrix integral, which just imposes confinement. But do I understand it right that part you're not doing? You're not integrating over Qs and Rs and so on. Okay, so in that sense, then it's a bit like studying some kind of a chiral Yukawa theory in some in thermal at finite temperature,
yeah,
and with some Polyakov Wilson line. So basically a Wilson line.
Yeah,
right?
exactly.
Okay,
Exactly.
okay. And but where did the Qs and Rs go in your the phase diagram that you're showing?
Okay, so
what did you do to them to get these phase diagrams? Yeah,
so,
all these diagrams, where are you have set Qs and Rs to something? Or?
Yeah, so I guess the Polyakov, I mean, say the Polyakov loop will be this one, right? I mean, the Qi and R are like here I have denoted as Qi and Qr. So we have the total potential. So while calculating the we can calculate the susceptibility. I mean, we can doing the double derivative of the potential with respect to Q and R. So and like usually we get the.
But the answer will depend on Q and R. So,
yeah.
So you've set Q and R to something to get these plots.
Yeah. So
what have you done? You have you minimized the potential or something?
Yeah. Minimizing the potential, we get some values on Q and R, then I feed that to get the other plots as well.
Yeah, so when you minimized it, did you take into account that there's some Vandermonde factor, right? You know, like when you kind of diagonalize this thing.
Yeah.
Did you minimize it with the Vandermonde factor or without the Vandermonde factor?
Okay, I'm not sure about the Van der Monte factor, but the thermal Wilson line is our diagonal in diagonal form. So if that
Okay,
answers it.
okay. Maybe I'll catch you.
Okay.
After this talk.
So one comment is that there is no gluon needed because he has defined an arbitrary another background field. So he is basically taking it first arbitrary, then comparing with the mass and other physically observable properties that defines the Q and R, and that basically sets the alternative field, alternative to gluons. So that is basically self-sufficient. There is no need for another extra background field.
No,
Okay, there is no need for it. No need for another background field. So I am asking that till now, whatever quantity, maybe thermodynamic or anything you have calculated, have you found any inconsistency with lattice or other established results? Because your theory is, I think, the best in the till now, whatever is available.
basically, I mean, we had to take some help from the lattice also. Like we had.
You are basically comparing with the mass or other observable quantities and basically fixing the Q and R. So that's what you are doing. After doing that, are you having any discrepancy whether you are having 10 quantities which are agreeing with the previous results of other models and some one quantity or two quantity that is not showing good
No,
behavior?
not till now. I mean, at zero temperature.
Everything is fine.
calculation, I mean, the zero temperature plots are there in the paper by Pisarski and Skokop. You can see that, I mean, quantities are fairly agreeing with the lattice.
Okay.
So, yeah, I mean, for the finite variant chemical potential, we have not yet done that, but zero chemical potential, it is fairly agreeing.
Okay, so then the thing, how much your theory succeeds depends on what type of repulsive and all these things you consider. So that's how you model it. So if you can model it, then your theory is perfect.
Hopefully.
So in this model, is there no ultraviolet divergence coming due to the finite temperature?
Yeah, the divergence will be renormalized. I mean, like
in this model, because it is every model depend on some cutoff parameter.
Yeah, one cutoff parameter is this. Yeah, you will get some, but this is zero temperature calculation and finite temperature one.
I mean here this integral, is it ultraviolet?
No, this integral is not ultraviolet, but I mean, when you do the finite temperature calculation, you can separate the zero temperature part and the finite temperature part, and zero temperature part usually when it diverges, you get rid of it by renormalization.
And what type of phase transition you are seeing here? Is it a crossover?
Yeah, I mean, I guess for till now it's some it's continuous. There is no singularities I'm seeing. So.